Hello, Calculus and Vectors class. This is 6.2, Applications of Sinusoidal Functions and Their Derivatives. So I'm not going to go into a big long spiel at the beginning. We're just going to try some application because they are very, very similar to the types of problems that we've seen before, except now we're just throwing in some trigonometric differentiation. So we're just throwing in one more little trick. So the best way to go about doing this is to just jump in and try some. So example 1 says a power supply delivers a voltage signal that consists of an alternating current and a direct current component, where t is the time in seconds, the voltage in volts at time t is given by the function v of t equals 5 sine t plus 12. It's asking us to find the maximum and minimum voltages. At what times do these values occur? So it's asking us for two things. It's asking us for the maximum and minimum voltages, and it's asking for the times. So you're probably going to find with some of these that you may not be totally familiar with the type of problem that we're dealing with here. You might not have any background in electrical theory. You might not be a physics person. That's okay. As long as you can read through the problem, you're going to find some information that's going to help you. And the first thing that I want to point out is that it says maximum and minimum voltages. Now, maximum and minimum, we've seen that before. We just need to find that voltage function, and we need to set it equal to 0. Or set its derivative equal to 0, I should say. So we saw up top that v of t is equal to 5 sine t plus 12. So we're just going to take that function and we'll differentiate it. That's going to be, let's see, 5 sine t, that's going to be 5 times cosine of t, plus 12 is a constant, so it goes to 0. So that's all we're left with, 5 cos t. So next we're going to set that equal to 0 and try and solve for t. So let's see, we can divide out this 5, and that just goes away because we divide 0 by 5, divide 5 by 5 on this side. And on the left side, we're left with 0 equals cosine of t. So to find the time, we're going to take t equals the inverse cosine of 0. And we know for this, it's not just one single answer that you get every calculator. We can get multiple answers. We can get pi over 2. We could get 3 pi over 2. We could get 5 pi over 2. So 90 degrees, 270 degrees, 540 degrees if you're thinking in degrees. But you should know at least that the pattern does continue. So now we know where the maxes and mins are, what times they're occurring. We just don't know which ones are maxes and which ones are mins. So we're just going to use a bit of know-how. And if you think back, with any sine or cosine function, we always alternate between maxes and mins. So it means that either the odd-numbered ones are going to be maxes, or the even-numbered ones are going to be maxes, and the rest are going to be the minimums. So we just need to figure out which ones are which. So we're going to test out. A few of them. So we're going to take the first two terms in our sequence, and we're going to plug them in to that voltage formula, not the derivative, the original function, because the derivative is just going to tell us the rate of change. We want to know the actual voltage. So that's going to be for pi over 2, it's going to be 5 sine of pi over 2 plus 12. That's going to be 5 times sine of 90 is 1 plus 12. That's going to be 17 volts. So now for 3 pi over 2, that's going to be sine of 5 times sine of 3 pi over 2 plus 12. And that's 5 times sine of, that's 270 degrees. And that's going to be negative 1 plus 12. That's going to be 7 volts. So that means that the first one's going to be our max. And the second one's going to be our minimum. And so on and so forth. So, therefore, the maximum voltage is 17 volts and occurs at pi over 2 seconds, 5 pi over 2 seconds, 9 pi over 2 seconds, and so on and so forth. The minimum voltage is 7 volts and occurs at, that's going to be 3 pi over 2 seconds, 7 pi over 2 seconds, 11 pi over 2 seconds. So next part, determine the period t in seconds, the frequency f in hertz, and the amplitude a in volts for the signal. In fact, there's no calculus required for this part. It's all just review from advanced functions, hopefully. So the period is just how long it takes to go through one full revolution. And we know that for a normal sine or cosine curve, it's going to be 2 pi. And for this one, we don't have any horizontal stretch or compression inside our sine function. So it's just going to be 2 pi seconds. Or we could even say it's 6.28 seconds if we want to, but we like to keep things exact if we can. If it makes sense in the problem to have a decimal, that's fine, but for right now it's okay to keep it exact. The frequency is just the period, and we just take its inverse. So 1 over t, that's going to be 1 over 2 pi hertz. Oh, and by the way, sometimes people use the unit seconds to the -1 instead of hertz. So if you ever see that, that's what that means. So the amplitude, we can do that one of two ways. So you could look at the function and look at the value multiplied with our sine function, or we just take the maximum minus the minimum and divide by 2. That's going to be 17 minus 7 over 2, or 10 over 2, or 5 volts. So our amplitude is 5 volts for this. So let's try a different type of problem with pendulums. I'll leave this bit of background on pendulums for you to look through a little bit. But there's a few big formulas for pendulums. By the way, pendulums, if you're not sure what it is, it's any sort of weight on a string or on a rod that swings back and forth. So we can find a couple of things here. We can find the period using this formula here, where L is the length of the pendulum, and g is the acceleration due to gravity. And we also have this function here, which tells us the position of our pendulum. And we use in this formula, A is the amplitude, T is the time, and big T is the period of the pendulum. So example 2 is asking us to find the maximum speed of the bob and the time at which the speed first occurs for a pendulum having a length of 1.0 meters and an amplitude of 5 meters. So first thing, let's talk about the function that we have here. This is position that we have in the formula. So unfortunately, it's not what the problem's asking for. It's asking for the maximum speed. But we know that if we took the rate of change, the derivative of that function, that's the same thing as the speed function, because it's just the rate of change of our position, how quickly our position is changing, which is our speed. So if we can find that, then we're golden. But the problem is we have too many variables here. So let's try and eliminate some of them. We know the amplitude, that was 5 meters. And we have 2 pi t over t. Now, our derivative is with respect to little t. So we're going to have to find the big T. So let's try and do that. And luckily we had that formula, the first formula that we saw in the description up top. That's 2 pi times the square root of L over G. That's going to be 2 pi times the length of this is 1 meter. And acceleration due to gravity is 9.8. Now, if you want, you can try and keep it exact. The math will be a little bit tricky, but just to make our lives a little easier, let's round this off. And we're going to say that this is about 2.00 seconds is our period. So that means our pendulum swings back and forth and comes to its original position again every 2 seconds. So, by the way, I did not write this correctly. This is still h of t, not the derivative yet. So let's make sure we make that correction right now. So that's 5 times cosine of 2 pi times t over, and we said the period is 2, which means those 2's are going to cancel, and we're left with 5 times cosine of pi times t. So this is looking a little bit easier to work with. So that's the position function. Now we're going to take the derivative of that, and that is going to be, let's see, that's going to be a chain rule problem, right? Because we have an inside function and an outside function. Let's take the derivative of the outside. That's going to be, cosine is going to become negative sine, so that's going to be negative 5 sine of, leave the inside function the same, and then we're going to multiply it by the derivative of the inside function. So in this case, pi times t is a linear, because pi is just 3.14. So we're just going to take the slope, and that's going to be negative 5 pi times sine of pi t. So that is, let's call that v of t. So now we said that to find the maximum speed, we have to take the derivative of the velocity function and set it equal to 0. So we're going to take the derivative of that function, which we could also call the second derivative of h of t. Same basic thing. We're saying the same thing. So let's take the derivative of that function here, and that's going to be, let's see, take the derivative of the outside. The coefficient is, the constant multiple is negative 5 pi, so that stays the same. And then we're going to do cosine of pi t, and then multiply by the derivative of that inside function times pi. So now, when we put that all together, when we clean it up, it becomes negative 5 times pi squared times cosine of pi t. So now that we have that, we can set that derivative of our velocity, of our speed function, equal to 0. And we can try and solve. So let's divide out the negative 5 pi squared from both sides. On this side, 0 divided by anything is still 0. And it cancels on this side, and we're left with cosine of pi t. So that means that pi t, we can just reverse that, becomes the inverse cosine of 0. So pi t is going to be, that's going to be, let's see, inverse cosine of 0 is going to be, let's see, that's going to be pi over 2, 3 pi over 2, 5 pi over 2, and so on and so forth. But now it's equal to pi t, so let's divide up pi from both sides, and that becomes t equals 1/2, 3/2, 5/2. But since we like to deal with things in time with decimals, let's deal with 0.5, 1.5, 2.5, and so on and so forth. So we found the times where we can have a maximum or a minimum, but we're not sure which ones are maxes and mins. But we do know that we're going to alternate. So we're going to alternate between maxes and mins. So we're going to use that same trick again. We're just going to test the first couple, and we're going to find the speed at 0.5, and we'll find the speed at 1.5. So we're going to take, the speed function was this one right here. So let's use that. So negative 5 pi times sine of pi times 0.5. If you put that all together, it becomes negative 15.5 15.71 meters per second. And then for the velocity, the speed at 1.5, it's going to be negative 5 pi times the sine of pi times 1.5. And you should get, in this one, that's going to be 15.71 meters per second. So it looks like our minimum is going to be negative 15.71 meters per second, but our maximum is 15.71 meters per second. So that is going to be what we put in our concluding statement. Therefore, the maximum speed of the pendulum is 15.71 meters per second. So a little bit tricky, but as long as you use a bit of know-how, use your differentiation rules, and just a bit of logic about periodic, sinusoidal functions, then it's not too bad. So happy practicing, and I'll see you in 6.3.